Hello together. Today I want to talk about the S parameter and how to use the S parameter to describe BJTs and field effect transistors. In the lectures before we saw that above around about 10 megahertz Y parameter are no longer appropriate to describe the linear behavior of BJTs and field effect transistor, which are essentially nonlinear, so these parameters are only valid for small signals, and so we will use then the S parameter to describe the linear behavior of our BJT. And of course these S parameters will be functions of the frequency and of course of the point of operation. This means they are, if I have a BJT, then we have the voltage UCE and IC as parameter, the DC values, and also in the case of the field effect transistor, we'll have the voltage U drain source and the drain current as parameter. So these S parameters will depend on these values, and in this video I will demonstrate first how to download my simulation tool, and in the second step I will use this simulation tool to display the S parameters of a certain, in this case, gallium arsenide field effect transistor. And so we will go on.
So before you can use my simulation tool, in the first step you must download the simulation tool from my YouTube channel. So to proceed, we go to my YouTube channel, and in the YouTube channel, on the page of the YouTube channel, you will find the description of the channel, and in the description of the channel you will find my home page, and then you click to the home page, and in this home page are different things given, and one thing is here the simulation tool. So if you click on this simulation tool, you will find the simulation tool itself. It's a zip file, and on the other hand there are also given some S parameter sets which are also given as zip file, and you can download the zip files. And to use, of course, this simulation tool, then you must unzip the simulation tool, and then you will have the exe file, and this exe file will run on Windows 10, or I can say it's ready to run on Windows 10, and the best resolution would be this resolution for the screen. And as soon as you start the simulation tool, then you can also simulate the problems I show in my videos. So now I want to show you how to use my simulation tool. So first you have to start the simulation tool, and then it looks like this. We have here a certain kind of circuit board, and on this circuit board are a lot of points, and there are some elements, and all these elements can be put on this circuit board. And to simulate today our gallium arsenide field effect transistor, we use the element network dataset, and we place the mouse arrow next to a point, and then we can tear up this network dataset. And this network dataset uses a so-called S2P file, which means scattering parameters of a two-port, and these are so-called touchstone files. And of course we can have a look to the touchstones file itself. And in this touchstone file describes a semiconductor, a gallium arsenide field effect semiconductor of Mitsubishi. And it is a low noise gallium arsenide field effect transistor and the S parameters are given in the range of 5 to 12 gigahertz. To get these S parameters, you have to bring the field effect transistor in a certain point of operation with a voltage of a drain source voltage of 3 volt and a drain source of 10 milliamp. And the dataset is organized like this. In the first column we have the frequencies, and then we have the parameter S11, S21, S12 and S22. And always we have the magnitude of this parameter and the phase, and magnitude and a phase and so on. And this is now our dataset, and of course if you want to analyze this dataset, it makes only sense to use the frequency range which is given here. So in our case it would be, we can use the frequency range from 0.5 to 12 gigahertz. So this is our dataset which describes our field effect transistor, and as the measurement equipment we use a network analyzer here, and we click to the network analyzer, and then we can also open this network analyzer, and you see both elements are connected to the ground also, and this is a symbol for a coaxial transmission line. So this is the inner conductor, and you see the outer conductor is connected to ground. And to connect the network analyzer now with our dataset, we just pick up a connection here, and we can hear this connection. Now of course this is port 1 of our network analyzer, and this is port 2. Always where you start is port 1, and where the end of the network analyzer is port 2. And we again take now a connection here to connect our network analyzer to our dataset. And before we now do the analysis, we will change the frequency range. Of course the starting frequency we can use as 1 gigahertz, but the stop frequency we must change to 12 gigahertz because only the dataset is given up to 12 gigahertz. And then we can do the analysis, and here in our first diagram we have the S parameter in a so-called log-mag diagram. This means the absolute value of S11 is given in a dB scale here. So more familiar we are at the moment with the Smith chart, so I will display this network analyzer also in, not a network analyzer, but S11 in the Smith chart. And of course we can also here use the marker, and we have here the start frequency of the marker, 1 gigahertz, and we can move the marker along this transmission line, or not along this transmission line, but along this path of S11. And you see for low frequencies the parameter S11 is capacitive, and it will change its behavior, and at a frequency of round about here where we are here, round about 10 gigahertz, we have a series resonance frequency, and then the input becomes inductive. We can also have a look to another parameter, for example S22, which makes also sense for to have a look on to the parameter S22 in the Smith chart. And also here you see now the difference to the S11 is that S22, which would be the output reflection coefficient, or which is the output reflection coefficient of our transistor, and it will be over the whole frequency range, it will be poorly capacitive. As a further parameter, we can have, for example, a look. Now perhaps I change this here. First I change the format to log Mac again, and then I have a look to the essential parameter of a transistor, which is the S21. In principle, this is responsible for the amplification of the transistor, and we can have a look here with the marker function, and we see, for example, that at 1 gigahertz we have S21 a value of 11 dB, which is of course greater than 1, and so this transistor will do an amplification over the whole frequency range. But we will see later in the lecture that we must go into more details to decide what will be really the frequency, the amplification we can get from this transistor. A very unwanted parameter is the parameter S12. It is the parameter which describes the feedback from the output to the input, and usually in the ideal case this parameter should be 0. So you see the feedback is quite small, starting at 1 gigahertz with minus 30 or better than 30 dB, but it will become greater with increasing frequency, and this parameter will be responsible for the point that some transistor may become unstable in a certain frequency range, but this also we will see later. You have also the possibility, for example, to have a look to this parameter in the log polar display, which also shows the phase of this parameter, and also we can use here the marker function, of course. And you see here, this is the 0 dB line, which means now we are below 0 dB, and only the parameter S21 will be greater than 0 dB. So we have here the reference line is this green line, and this is 0 dB, and we have a 10 dB per division. Of course, we could also change the scale to, for example, 5 dB per division, and so you see that this gallium arsenide field effect transistor is able to give you an amplification over the whole frequency range from 1 GHz to 12 GHz.